Alright, we're going to talk about 7.5 today. Talk about roots and zeros. There's a couple methods of finding out, how many different kinds of roots you have in a certain polynomial function. So before we get into that, I'm just going to kind of go over some facts here. Any polynomial of the nth degree has exactly n roots. They could be all of this form. So that means you could have positive real roots, negative real roots, or imaginary roots. And notice that imaginary roots will always come in pairs. So that means you'll always have a plus or minus I squared to 2. Okay, so your imaginary roots will always come in pairs. Not necessarily your positive and negative, but imaginary you will. So if you have one of them, you also have to have the other, and I'll explain that here later on. But so that's the idea. We want to try to find those roots. That's kind of where we're going to get to a point where we find a way of solving big polynomial functions like p of x here. Okay, so the first technique that we're going to use here has to deal with trying to figure out how many positive roots we have, how many negative real roots we have, and how many imaginary roots we have. And that's using the Descartes rule of signs. So my first thing I need to do is I want to make, and this is using Descartes rule of signs, I want to make a table. Okay, that wasn't very straight. Okay, so to figure out the positive roots, how many possible, and these are scenarios that could possibly happen. Okay, so I want to analyze what p of x, how many sign changes there are. Okay, so for example, just the regular function itself, p of x. So do I go from negative to positive? Yes, I do here. That's a yes. Okay. And then positive to negative, that's a yes. Then there's negative to negative, so no. And these are sign changes. I'm counting the sign changes. So here I lost track. And then, and that's a no. So, and how many sign changes I have here, and this particular problem is in the original function p of x, I have 2 sign changes. So what that gives me here is 2 possible positive real roots. Okay, and then it decreases by 2, or by an even number. So I either have 2 possible positive real roots or 0 positive real roots. It always decreases by 2. All right. So I know for a fact that I'm only going to have like 2 rows or 2 scenarios that I'd have to figure out here. Now to figure out the negative column, I need to figure out what p of negative x is. Okay, so I analyzed p of x, I figured out this column. Now I want to figure out what p of negative x is. I need that. So basically, I'm just going to plug in negative x into the function and reevaluate it. So negative x to the 6th is actually be a positive x, but then this negative sign out front is going to tag along with it, so it doesn't really change itself. And then I put negative x in here, it's going to be a negative x times 4 will be a negative 4x. If I put a negative x in here and I square it, there's not going to be a sign change in there. So notice that if I put a negative x here, that's plus x, and then your constant is 1. So notice when my powers are even, my sign doesn't change, especially, my sign doesn't change. And then when the powers are odd, my sign changes. So that's really key there. You have to make sure you kind of look at the pattern on that. Now I want to count my sign changes again. So here we go. Just count my yeses. So this is a no. This is a no. Yes. Yes. So here's a no. No. And then it goes from negative to negative, then negative to positive. So this is a yes, and then a positive, negative. So this is a yes. So in this case, it's 2 as well. And then I also have 0 here. And then I guess, so there's 2 possible scenarios, and I forgot to add 2 more columns to the list because there are another combination of what this could be. So after analyzing that, your P of negative x, and you realize that there's still 2 sign changes, so similar to what we did up here. Then you have 2, 0. I guess the other part of my table that I forgot to include here is probably the other combinations of what these could be. So for example, I could have 2 and then 0 and then 0 and then 2. So actually there's 4 possible scenarios that's going to happen here. All right. Now, so now the easy part is actually this last part, and that's trying to figure out the imaginary solutions. If we did the tricks to figure out the positive roots and the negative roots, now it's to figure out the imaginary roots. And if you haven't noticed, to the nth degree, this rule up here, if it's to the nth degree, it has n roots. So if it's to the 6th degree, that means you have to have 6 roots. So your rows should always add up to be to 6, or to the degree of your polynomial that you're figuring out. So in this case, I have 2, well this has to be 2. In this case, in this scenario, if I have 0 positive roots and 0 negative roots, that means I have to have 6 imaginary roots. And then this would have to be 4, and this one would have to be 4. So this table would analyze or give you possible solutions or scenarios of what your roots could be. But just by doing this, Descartes' rule of signs, I know for a fact that I don't have more than 2 positive roots, and I don't have no more than 2 negative roots. I am going to have imaginary roots for sure. Okay, it's going to be a must somewhere in there. Is it going to be an imaginary root? So just by analyzing that table, I can figure that out. All right. All right. So here's an example. The instructions here says find all the zeros of f of x. So I actually need to find all the solutions, that's going to make this true. So I'm going to make this thing equal to 0. And that's my goal here. And I'm going to use Descartes' rule of signs to help me out with that. So first things first, analyze my sign changes here. I go from positive to negative, so that's a yes. Negative to positive, so that's a yes. Positive to positive, so that's a no. So it becomes 2, 0 for that. But then, below that, I want to go f of negative x and do the exact same thing. And remember, if it's negative, I plug negative x in and x cubed, it's going to change the sign. But if it's squared, it won't change the sign. So I end up getting something like this. So this is no, no, yes. No, no, yes. So, it's exactly 1. And when that happens, it's just, 1 all the way down through. Because you can't go down by even numbers. So the only scenarios that you can have is 2, 1 or 0, 1. Which is good. So, and then your imaginary possibilities, then, well, this already adds up to be 3, so then this would be 0. Remember, your rows have to add up to your degree, so, and that's how many possible zeros you have for this polynomial. And then in this case, this has to be 2. So, it's either this case or this case. You know for a fact, though, that there is a negative 0. So that is what I would try to do then. I'd try to find that 0 by, doing synthetic substitution. Because we are good at doing that, and it should be pretty quick like. So, and it's negative, so it has to be a negative number. So what I would probably do is I would start with, your negative integers. So now I'd start with -1, and if that doesn't work, go to -2. And how do you know it works? Well, if you do all your substitution, what should your remainder be down here? Well, it should be 0. Okay. If this is a 0 of the function, then that means x plus 1. In this case, it would have been x plus 1 would have been divided into this polynomial evenly, and it would be a 0 to the function. So this remainder has to be 0. So let's see if this works. And this is to my original function here. So I have 1, -1, 2, and 4. Bring down the 1, I get 1, and then I get -1. I add, I get -2. I get 2, I get 4. Oh, look at this. And then -4, and then I add, I get 0. So it just happens to be that -1 is my root. Now, I didn't plan that out, actually. I just kind of took this problem out of the book. So that actually turned out to be a fairly easy problem. Now, sometimes, if this wouldn't have been 0, then I'd have to go to -2 and keep trying to find it. Sometimes it's pretty tedious, pretty tedious work. The reason why I chose to try to find